Hi, and welcome to This Week in Science and Technology. In the past 3 episodes, I showed that relativity is a failed theory. Specifically, I showed that Einstein's spherical wave proof fails. His equations are an approximation of modern mechanics, and relativity produces answers that have less than a 1% chance of being right for the Michelson-Morley experiment. Now that we know that relativity fails theoretically and experimentally, and that another theory produces equal or better answers, it's time to turn our attention to modern mechanics. Today, and in the next few episodes, I'm going to introduce you to modern mechanics, its key concepts, and its core equations. So let's jump right in. Imagine a street, and on the street is a bus. Standing next to the bus is a man. These are the only objects we need for now to introduce you to the key concepts. But to build modern mechanics, we have to introduce a few constraints or rules. First, the street never moves. Second, both the bus and the man can move. The bus is either stationary, which means its velocity is 0, or it's in motion at a constant velocity, which we'll call v. The same applies for the man, but we'll call his velocity w. Third, the bus moves in one direction, which we'll say is from left to right. Fourth, the man has one job. As he walks in the street next to the bus, he must walk from the vehicle's rear bumper to its front bumper, then turns around and walks back to its rear bumper. Upon reaching the rear bumper, he has to do it all over again until we say stop. This repetitive back and forth cyclical behavior has a name. It's called oscillation. Now, believe it or not, you've just learned the key concepts associated with modern mechanics. But let's introduce some terminology so that we're able to generalize these concepts. This is important because if all we can explain is the behavior of a man and a bus moving along a street, we wouldn't have a very useful theory. In modern mechanics, things or objects are referred to as systems. In our example, we have 3 things: the street, the bus, and the man. The street is called an outer system. It serves as a reference against which we can measure things, like the location of the bus or how far the man has walked. Anything placed on or in another system is called an inner system. Since we place the bus on the street, the bus is an inner system. Notice that when we place the man on the street, he is also an inner system. To avoid name confusion, we will describe the man by his behavior, which I mentioned earlier is to move back and forth between the 2 ends of the bus or inner system. So we'll refer to the man as an oscillating system. So, in its simplest form, modern mechanics consists of an outer system, the street, an inner system, the bus, and an oscillating system, the man. One more thing. In our example, we place the man on the street. He was standing next to the bus. We call this relationship where both the man and the bus are placed on the street a non-nested relationship. But notice, we could have easily placed the man on the bus. This creates a unique situation where the bus is an inner system with respect to the street, but an outer system with respect to the man. This is called a nested system relationship. For now, we're going to focus on the non-nested relationship where both the man and the bus are on the street. This will allow us to develop some interesting equations and also later highlight some of the mathematical and conceptual mistakes found in Einstein's work. Now I have some good news. You've just learned the key concepts associated with modern mechanics. In the upcoming episodes, I'll develop the math that goes along with this model. And as you'll see, the math will work as you would intuitively expect it to work. And that's where we'll begin next time, as I continue to introduce you to modern mechanics. Until then, I hope that you'll continue to explore my blog and videos, and will begin to share what you're learning with others. Until then, I'm Stephen B. Bryant, and that's This Week in Science and Technology.